All right, so yeah, thank you very much to Sanadu for the invitation, and it's a pleasure to be here. It's a real pleasure. So what I wanted to tell you about today actually is something that has been in my mind, in particular in the last 14 years since I started my PhD, and it's about actually how can we make an impact with these quantum computers in the case of real-world applications. And I will try to give you, hopefully, towards the end of the presentation, you will get a gist of actually what I mean by this. Actually, it's a very applied, but still kind of like very grounded approach to developing algorithms for real-world applications. So the very first question, actually, that we've been asking ourselves, and we still don't have a completely answer, to be honest, is what is the power of quantum machine learning models? So we won't be addressing that today. I mean, I think it's a super fascinating question. I'm super interested, and you will see some papers coming out from the team as well in the coming months. But in reality, what I will be focusing today is in the applied perspective. So how can we make an impact with non-obvious applications? So what do I mean by non-obvious? So what are the obvious ones in my mind? So the obvious applications in my mind are, for example, quantum chemistry. So we know we have a quantum system match with the complexity of the quantum computer. So you should expect naturally a quantum speed up in those type of applications. Of course, I mean, if another potential candidate is even in quantum machine learning, if you have a quantum system, you have a quantum generative model, of course, I mean, there is a match in the complexity there where actually that could be another area that is a bit more obvious. The one that is still a gray zone, and that's why it's still fascinating to me, and it's been taking me 14 years to go from application to application in this search, is okay, what about industrial applications? What about actually, for example, like logistics and planning, protein folding, for example? That was the very first example that I did in my PhD. How can we do lattice protein folding with a quantum device? How can we do portfolio optimization? How can we do NASA-related problem, detecting faults in electrical systems? All of that is what I'm going to be talking about today. So I'm going to narrow the focus of this discussion just to classical machine learning or classical combinatorial optimization with quantum computers. So I just wanted to set the stage of that. And I will try to give you an idea of where and how to approach this question, or at least from our experience. I will provide a couple of examples. So you will see an example of recent work, in particular in the case of generative modeling in unsupervised machine learning. And the other area that actually, it came as a surprise, but I think I've been kind of like in a hate and love relationship with combinatorial optimization, I think I came to a really nice marriage in the last years, I would say, where actually I could combine them both, machine learning and optimization, and see actually that they can actually reinforce themselves. And that's actually the very recent work that we just posted a couple of weeks ago, and that you can find in the archive. So hopefully at the end of the talk, you will get an idea of the importance of these novel algorithms, the impact of software, the impact of having access to hardware and the development, in order, if you're really interested in this question of practical quantum advantage. Notice that I'm deviating from the standard computational quantum advantage, or also so-called quantum supremacy, in the sense that I'm interested in industrial applications. So I'm interested in something that is relevant, something that is useful, and that we can show actually that is going to impact industry, for example, the industry sector. So now let's move and actually dip to the first question of where. And I was facing this question also when I jumped. I think Juan Miguel mentioned that I was one of the pioneers, but I would say I came in the second wave of, I was working combinatorial optimization since 2006, but I think in principle, I joined the wave of machine learning about 2014, so about 7 years ago. So I would say it's the second wave, and it's the wave of actually, what I feel actually, I see the community picking up more interest is in the intractable problems in machine learning. Not just quantizing every single machine learning problem that exists from PCA, support vector machines, not just quantizing that and say, oh, cool, actually, we can do this with a quantum computer. I think that gave us a lot of insights, so it was super valuable research. But I think now, when I was facing this question and I was at NASA, and I was forming the quantum machine learning team at NASA, I would say, okay, so I feel that actually, if we're going to use a quantum device, we better search for the most difficult problems in machine learning. Why? Because machine learning experts, they're doing quite well with the supervised learning side. And I think you can see that actually, it was in 2014, but you can see this was reinforced. And I was actually happy to see this from Yann LeCun, Joshua Benjo, and Jeff Hinton in this quote from Nature, where they say that basically unsupervised learning, and in particular these generative models, has been overshadowed by the successes of purely supervised learning, but we expect unsupervised learning to become far more important in the longer term. And this is basically, as you know, this is actually how we humans learned. So we don't have an instructor and a teacher every single time. We just learn by experience. We just learn by seeing data, by being exposed to data. And that is not a label every single time that we're experiencing something new. So this is the most difficult. This happened to be one of the most difficult cases for machine learning. And of course, I mean, it would open a lot of applications, in particular, more like general artificial intelligence type of applications. So this is actually what we decided to tackle when I was making this decision with my back then master students, Marcello Benedetti, and he joined us as an intern. So the focus of this talk is going to be in the particular case of unsupervised machine learning, in particular generative models. And the motivation behind that is just because my interest was just in the case of making an impact in the nearest term, not actually waiting 30 years, 10 years, 20 years. I just want to see if I can make an impact right now. And to do that, I need to find out where the classical machine learning experts are struggling. So that's the story, actually, how everything started in my mind, or why to even decide for this particular application. So let me just actually quickly walk you over the difference. I mean, I noticed in the very first talk this morning, there are a large percentage of newbies in the audience. So let me just give you the difference between supervised machine learning and the case of unsupervised, and then jump into generative models. So in the case of supervised machine learning, what you find is actually you have a data set, but the key feature of supervised learning is that you have the label the data is labeled. For example, you have here 3 pictures of dogs, 3 pictures of cats. Well, this is kind of like I think it's mysterious cat, large cat. But then basically the question here is different. The question in supervised machine learning is simple. It's actually, if I give you a new image of a dog that is different from those ones, the AI or machine learning model should tell you, okay, that's a dog. So it's what we call discriminative task or classification. Is another name for this particular type of task. So notice here, the important thing is the data is labeled. In the case of unsupervised machine learning, as the name indicates, unsupervised is just that there are no labels, but you just have the data. And basically an example of this is clustering, where actually, basically you are supposed to learn correlations between the data and tell these ones apart. And just to understand that, for example, all of these can only belong to the vehicle type of class, and these ones are the dogs, and this one, the cats. So that's basically unsupervised. The one that actually grabbed my attention the most was this particular class of within unsupervised learning that is called generative machine learning or generative modeling. What is the task there? It's much more difficult, and as I said, it's one of the most difficult tasks. And it's basically if I give you actually an input for a dog, after showing you maybe many pictures, the AI model, the machine learning model, is supposed to be able to paint or to generate what a dog actually looks like. So this is just from just observing the data. So for those of you actually who are more familiar with the machine learning models, you can find this in the very famous kind of like a work of generative adversarial networks. So that's a generative model. You can find this in restricted Boltzmann machines, or more general, it's called energy-based models. So you can find that, or variational autoencoders. So some of these actually we see nowadays in machine learning papers all the time. If you want to have fun actually with the generative model, so go to this website, thispersondoesnotexist.com. Maybe do it after the talk, and you will find actually a lot of faces that from people who does not exist. Basically, completely new faces generated by an AI algorithm that you can find there. And in the quantum regime, actually, there has been also some interest. For example, there is the work on quantum GANs, there is the work on quantum Boltzmann machines, and there is the work also, for example, another framework for exploiting probabilistic modeling in machine learning is the quantum circuit board machine. We'll tell you a little bit more about this in the next slides. So now, let's deep dive a little bit more about quantum in generative models. So where do we have an opportunity? As I mentioned, I came mostly kind of like in the second wave. In the first wave, I will classify those algorithms, and we still see them today. But the first wave of algorithms as well, they are targeting more like fault-tolerant quantum computation. And also they were interested in the question of loading all the data and using the quantum algorithm as a whole. So the approach, and again, it's coming just because I wanted to be very practical, is what I decided to adopt with the team was this hybrid paradigm that now is very widespread. and it's pretty much what we do with these variational quantum circuits, is just to leverage as much as we can on the classical resources. And there are many ways to do that. And that's what I wanted to give you a brief perspective of how this works. So for example, you can have an intractable machine learning model that you're trying to train. Basically, you have a training data. You're trying to train the classical model and the predictions. So this paradigm in particular that I call quantum assisted classical machine learning is when you make calls to the quantum device only to solve a specific subroutine within the classical pipeline that is very difficult to solve. For example, if you're training Boltzmann machines, you will like to do just the piece of a stochastic gradient descent that is very complicated to do because maybe you get trapped in local minima. So thus, you want to isolate actually where the difficulty is and send that as a subroutine to the quantum model. But then notice the big difference here. The model at the end of the day, the resulting model is still classical. The only thing is that I'm using the quantum device to assist the process of the training because the training is one of the most important pieces in machine learning that people sometimes disregard. So, but training could be actually very difficult, and that's one of the most difficult things. It's not about the model expressibility, it's sometimes the path, how you get there. And that's the training piece that is very important. So this is actually, when we jumped with Marcello, we were thinking, okay, so let's see actually what's in the literature. And it was to our surprise actually since 2010 that there was a paper proposed by the D-Wave folks about how to do this. There was actually not a single contribution actually doing this as an experiment. There were a couple of papers more like on the theoretical side, but we realized, why is that? I mean, at NASA, we had a D-Wave device. Why is that actually that nobody has even done an experiment? And the crux there lies that actually doing this with quantum devices is not completely straightforward. And I invite you to take a look at that paper. But basically, if you're doing that with a physical device, you really need to understand the dynamics of the system in such a way that that system can help you in the classical training. So matching the classical and the quantum complexity, the physical model and the classical in silico model is not always straightforward. That's what we learned from that paper. And we needed to find a way to solve the puzzle that was phrased in this 2010 paper that was needed to be able to overcome that barrier. So that's actually how you can do quantum-assisted classical machine learning. At the end of the day, you end up with a model, classical model that you can just make queries. But in the meantime, you use a quantum device. The second paradigm is what we call this classical assisted quantum machine learning. And I would say maybe the very first paradigm that kind of like shifted the attention to the quantum model is this paper on the quantum Boltzmann machine. The reason here, the paradigm is not the model doing the job. The one actually that you're going to query for answers is quantum in nature. So I think that's what is special about this quantum Boltzmann machine. And basically, you're restricted here to Hamiltonians and to thermalizing systems, quantum systems that you're trying to thermalize, and you're using that as your model. But it could be a quantum model. So that opens kind of like a new perspective on using, expanding the Hilbert space from going just from the classical type of probability distributions that you can easily access with a classical device to the quantum regime. And basically, I mean, I think that's I think the idea that we propose in these quantum circuit Born machines is we realize actually, I mean, there is a lot of space in the Hilbert space to represent probability distributions. Every single state, every single wave function is a probability distribution just because of the probabilistic nature of quantum mechanics. We even have a name for that. We call them Born probabilities, when we look at the amplitudes of each one of the possible measurements in quantum mechanics. So quantum mechanics is probabilistic. And all the things that we propose in this paper with the quantum circuit Born machine is just to do a natural marriage with a kind of a variational approach, hybrid approach, where you can leverage on classical resources, how you can actually come up with probabilistic models that live within a wave function. So the wave function itself is the Born machine. That's actually that was the name that was adopted from a previous paper that was doing the same, that proposed actually in parallel to our work in the case of tensor networks. So that's basically what we propose in this paper. It has been actually implemented, I mean, in about 5 different hardware architectures. And also there are beautiful extensions showing, and has been really a workhorse to prove, for example, the difference between quantum generative models and classical generative models, just to show actually that there could be usefulness in this particular quantum models. The last paradigm that I think is the one that I'm mostly excited, that I've been excited in the last years, is this is kind of like another phase that I would call machine learning assisted quantum machine learning. So your model is quantum, as in the case of paradigm number 2, but now you are leveraging even more on the classical resources. This was actually came from an idea that I was pushing my team maybe about 5 years ago. When actually I was pushing, I say, there is a beautiful idea in machine learning when you're doing variation autoencoders that actually that the data, when you pass through the deep network, the data is compressed, is embedded in some way. The representation changes of your data when you work in a deep neural network. What I asked my team is, how can we make the quantum computer work in that representation and not need the original representation? Because then actually we could do industrial applications with very, very near-term small devices. And that's basically the whole hybrid paradigm is really, really intertwined, where you can use state-of-the-art machine learning to pre-process the data, finally use a quantum model to get a boost, but then you can also use classical machine learning to post-process. So basically, you're just using the quantum device when it makes sense. Inside are actually a complex network that includes quantum and classical components. So that's what we propose in this perspective article, and that actually was extended in this particular framework. We even did an experiment, actually in a follow-up paper to that perspective article, where we show this idea. And basically, instead of working directly on the data, what you could be working is in this latent space. That's actually the key part, is the quantum device is attached to the latent space, to the data which has the lowest dimensionality, the reduced dimensionality. And then the quantum device is trying to make sense of that abstract representation of your data. The beautiful thing is that you can attach small devices here instead of using, let's say, the thousands or million pixels that an image might have. So that was the very first proposal. But actually, there has been a lot of exciting actually developments in this particular framework. In particular, for example, the NASA team proposed actually how to extend this in the case of GANs. And it was followed actually by a paper from Eric Anshues and Chris Sanoshi as well, where actually they use a similar idea, but actually with a quantum model in the latent space of a GAN. And that's basically, again, is the same idea of inserting a quantum model only in the latent space that we follow. In the case actually of supervised learning, it has been actually shown by the Xanadu team actually that you can actually for example, as I said, that's the only way that you can really access to real world data is by compressing the data, using a classical network, and then actually using a quantum device for the piece that actually that makes sense. So that's actually another example is in the case of the D-Wave type of devices. So this quantum assisted variation autoencoder had the same idea where the quantum model lives in the latent space. So actually this dense representation is actually the one that you're trying to capture with the quantum model. So again, I mean, the motivation here has been always, how can we squeeze that data that might be redundant? How can we squeeze that with the assistance of classical neural networks? And then we pass that to the quantum device. So that's the idea that we proposed back in the day that I think actually is very powerful to go to near-term devices. So with that actually motivation, I would like to transition to a specific example. I already mentioned the case of GANs. And actually the case, as I mentioned, this website, thispersondoesnotexist.com, there was actually a New York Times article that was featured in this particular, and this is, for example, if you go to the website, this is the type of faces that you will see. And these are actually completely generated by a classical machine learning algorithm, by a GAN-like algorithm. When you think of machine learning 101, you think of the MNIST dataset, so the case of handwritten digits. And this particular dataset consists of 60,000 images or digits, like these ones that you see here. In the classical domain, actually, the quantum domain with gate-based devices, what we found actually is that, this is the state of the art. It was published in October 2020 as we were working in our paper. And as you can see, with the small quantum devices, there's not much hope actually. This is actually very low resolution digits that you can get. This is number zeros and these are number ones. So the question that we asked ourselves that we were working already before this paper was published is, how can we leverage on that framework that we propose to do that? And how can we, for example, adapt GANs for actually doing this with NIC devices? So basically what we did is an adaptation of the work from Eric and Chris, where actually we propose how to do this with gate-based devices. And there is a lot of richness actually when you go, let's say, from a quantum Boltzmann machine to a gate-based type of circuit. One of the things that it was fun to do is, for example, if you're working with a quantum circuit, and the quantum circuit is the brain of your quantum model, you can actually leverage and enhance the resources of your probabilistic model by measuring in different computational bases. That's something actually that is unique, that is quantum, and that actually we show that that's how actually we got the best results in our simulation. So that was really a fun idea and really surprising. But the fact that you had these circuits and all the expressibility of the probabilistic model that comes in these measurements actually can be enhanced by measuring different computational bases, in orthogonal basis. And still, and this is the framework actually that we adopted, is still you can leverage on very, very complicated deep convolutional neural networks, for example, in this particular case of GANs. So this is actually a framework, and I invite you to go and take a look at the paper for the details. And there was a beautiful experimental realization of this work as well that you can find there. So this is actually the experiment that we did with the team IonQ. We did actually on their hardware. And what you can see is the simulations here. So briefly, what you see in the y-axis, the inception score. So the inception score is telling you the higher, the better. The higher, the better the quality of the digits, and also the more diverse they become. And what you can see is just a bunch of simulations from quantum simulations performed in silico to the two experimental cores that we observe here. We did another actually fun experiment where we even trained which bases you're supposed to measure in. So that was actually a beautiful idea, where instead of actually setting the bases that you want to measure, the orthogonal bases, you can just let the bases be decided by the machine learning algorithm. And that actually worked pretty well and is very robust. Actually gives a lot of robustness. And what we found is that when we compare to comparable GANs, state-of-the-art GANs for that particular framework, actually happens that the quantum enhanced solution, describing the prior with this quantum model, it was giving us a little bit of a boost. So how does it actually looks like from the digits compared actually, how does that improve the work from the state-of-the-art? So remember, actually, this was the state-of-the-art work from October. And actually, this is the work, the quality of the digits that we managed to get from samples directly processed from the quantum device. So this is the samples come in, it go actually through the neural net, through the deep network that is trained in sync with the quantum device. And then actually, this is the type of quality of digits that you get. So for the first time, we can generate high resolution digits on quantum devices. And we can, of course, move this to other exciting applications that actually of industrial size, let's put it this way, in generative modeling. So let me see, actually, I think I have like 5 minutes. So I'm going to skip actually for the most part this component of the software component, because I can invite you actually to take a look to a recent talk that I gave at Q2B, where basically you will learn that the main motivation for orchestra was to have the swappability, the scalability, be quantum ready, and be machine learning ready. So if you go actually to the digits example, what you will see actually is that behind the hood, actually, you will see that it's quite a complex workflow to get that working. Then you need to define the GAN, you need to define the prior. There is a lot of parameters that you need to specify for machine learning, run the experiments. All of that happens, and maybe there is just one piece that actually is the quantum component. All of that is very neatly integrated with the capabilities of swapping components. For example, we can change from a forest simulator to IonQ or Honeywell just by changing one line in the code. Actually, so we can we submitted these jobs to Honeywell at some point, and we also did the final experiments on IonQ. And this is actually what you can get just with the power of orchestra. So just kind of like the robustness and the swappability between different components. If you had, for example, code that works in Pennyline, for example, there was a recent integration with that. In the future, hopefully, we also will have TensorFlow Quantum, and then actually you can swap between libraries. So you can actually leverage, we already have Qiskit, we already have Cirq. So those are actually, you can leverage on all these different backends that would be available as well as in one place. So yeah, so let me actually skip. I will invite you to take a look at this particular talk. If you're interested more like the emphasis on that talk was more like in the software components. But it's extremely important to keep in mind that for delivering these scalable experiments and reproducibility, it's important to have a workflow management system as the one, that's what at least we see, that's the value of orchestra. And certainly we leverage on all the wonderful things that, for example, libraries like Pennyline or TensorFlow Quantum actually can offer. So now, briefly, let me tell you a little bit about quantum enhanced quantum enhancement in combinatorial optimization. As I said, when I was back in 2006, maybe up to 2014, before I started working in machine learning, my passion was combinatorial optimization. And then actually, came the machine learning bug. It was like about 7 years ago. And finally, actually, I was more optimistic about machine learning. But I think recently, or at least, yeah, so we've been working in this project for about 1.5 years now. Where actually, there was an idea that actually we could apply actually what we were learning about quantum generative models in the context of combinatorial optimization. And actually, to a surprise, it came really, really well. The results actually we're really, really surprised for the results. So I don't think I will have time actually to go through the framework, but basically what you are doing in a nutshell in this diagram that you can read in our paper that is already posted in the archive is that by inserting actually a quantum generative model that is trying to understand seeing solutions from, let's say that you're trying to solve a combinatorial optimization problem with the state-of-the-art solver. Let's say it could be a Bayesian optimization, it could be simplex, it could be simulated annealing, parallel tempering. You're just trying to solve an optimization problem. What we found is a way to get that information, doesn't matter where it's coming from, to feed that to a generative machine learning model, and that model has the power of proposing to you where are the next candidates that actually you should be sampling. So that was a crazy idea. I mean, I thought at the beginning, but actually it turned out to work actually pretty well. Let me show you actually, and this is, I think that what I find more fascinating about this plot is something that is, if there is a property that is the most desirable property in any machine learning model is generalization. And what that translates in the case of generative models is to be able to generate, for example, if I'm training with faces, you don't want to memorize the faces, you want to generate new faces. If I'm giving you some samples from some portfolio optimization instances, some potential portfolios, and I'm giving you that, I don't want your model to memorize those portfolios. I want you to generate new portfolios, to generalize. And this is for the first time, actually, we're showing that these quantum-inspired models built out of tensor networks, in this case, a matrix product state, they actually generalize. And not only generalize, not only give you a plethora actually of new candidates, that's actually the orange line here, but actually all of these candidates happen to have even lower risk and therefore more return actually, or more a better solution in the context of portfolio optimization. So this is actually something that is super exciting because for the first time we are using this problem in a real world application. The x-axis here is the risk. You're trying to minimize the risk. And this is the count of number of portfolios that appear from the quantum model versus the one coming from the classical data. So this is really a remarkable thing actually to show that actually in a real scenario, these quantum-inspired models, generative models, do actually add value to the search. And that's how we actually managed to beat the classical solvers and use this as a booster, as a quantum enhancement. And you can see the details in the paper where we present all the plots and all the details of the algorithms that we use. So with that, pretty much, I think I'm almost close to my end. So just to wrap up, so I hope, you got an idea about the possibilities in real-world applications with these near-term devices on quantum models in general. I presented two cases. The case of generative model addresses one of the many difficult questions that you might like to address with quantum machine learning. You're about to do a hackathon. So my advice is challenge yourself with a difficult machine learning application. Try to find something that actually might be worth to do that quantum computers can have an impact right now. So, but of course, if you're just learning and you're actually exploring foundation idea, trying to understand the models, of course, pick something that actually is good for you. But let's say if you're interested in this question of quantum advantage, my advice is always just go for something that is the most difficult task, the intractable task in machine learning. So there is actually another work that I didn't have a chance to talk, but the paper should be posted in the archive soon. And this is actually goes to Patrick was giving this wonderful talk about all the results that they obtained and the Google team has obtained about pattern plateaus. So we have a new technique that is based on machine learning and that actually resolves or mitigates this issue of the pattern plateaus, not only in the cases that have been reported in the literature. As you can see from these plots, actually the variance doesn't actually just completely vanish, but actually with the machine learning technique, you can manage to maintain the gradients. But also we tested this in the case of optimization, in the case of chemistry, and also we showed that actually this technique is completely flexible in the sense that actually you're not restricted to use it for circuits of a fixed size. So for example, you can predict which values you should initialize when you even have an ansatz, let's say, with larger number of parameters than the one that you train with. So it's basically, it's just machine learning. I think Patrick was mentioning about the need for thinking about the design of this. And there are many, many things that you need to tweak. So basically here, we're letting the machine learning model to decide for us what is actually the regime where you want to initialize these parameters. So finally, I think it's just a final point that I wanted to make across as part of the motivation for this domain, and it's the importance of the talent. I think in principle, any of this work, I think it could not be possible with the team actually that we've been building and that actually has been contributing to a lot of this work in many, many different. So it's really, I mean, the work in my team is very, very kind of like cross different topics. So it's really hard to put actually colors to each one of these boxes. For example, we have someone like, for example, if I think of Matt and Marta in particular, they're working mostly in the software tools, but of course, I mean, they're building these new techniques and also doing a little bit of research and exploration. So although most of their work, they're working on the software components, they're actually doing as well research and pushing this actually implementing these techniques and pushing it to the next level. And of course, I mean, I think in our case, one advice that I have is just mingle with people from the machine learning community as much as you can. If you're from quantum physics, quantum algorithms, mingle as much as you can from machine learning. That's something that I've been doing, I think, for the last 7 years. My PhD student, Marcello, who graduated from UCL, is from the computer science department. Luis Serrano, for example, who we brought from Apple, and he was the head of content in AI in Udacity. He was coming from a completely entirely machine learning background. So, for example, Javier is coming with a PhD in physics, but then he worked for 10 years in the finance sector, in banks, directly in London. So this is the type of expertise that really will foster innovations in this field. So it's a very, very young field, I would say, regardless that it's been going on like for about 12 years or so, let's say since 2008. Let's say that we had the very first developments in QML, like more consistently, I would say. But then in reality, that requires a lot of different expertise. And definitely, I mean, this is the talent that I would say I'm very grateful. And that basically is the people actually putting this work that we've been generating in the team in the last year or so. So if you have any questions, so I'm happy to answer any questions. So thank you for your attention, and thank you again for the invitation. Oop, I think
you're muted, Monk.
I was muted. It's part of the fun of talks. It has to happen. I was very careful not to talk over Alejandro. So I was saying, thanks again for the fantastic talk. This was really great. People in chat were very impressed, myself included, with the high definition of those MNIST digits. So Alejandro, the way this is going to work, there were some questions from chat, and I guess some of them might be coming right now as well. So we're just going to do a Q&A, and then I'm going to have some fun afterwards. So there's a question by Quanteric. Actually, a few questions, but I'm going to try to summarize them into just one. So they're asking, what are the practical limitations of the gate model, generative models, compared to using quantum annealers?
The practical limitations of gate models. Well, I think, for example, we've been finding, and it's interesting because let's say I worked with quantum annealers for many years. And the reason to be honest, I just swapped is because I was just curious to explore and go more in depth actually in quantum algorithms there. What I've been finding is, for example, with QAOA and all this kind of like heuristics, I think for optimization, I think at some point they're going to face similar issues with that the quantum annealers face. The quantum annealer is manifested in different ways. Like, for example, the noise in the quantum annealers, it could be actually quite detrimental, as it is in the case of gate-based devices. But I would say the trainability of these models, it's hard to tell, but because each one of them is a different Pandora box in some way. For example, Patrick was talking about, for example, the issue of barren plateaus in the previous talk. And that's one thing, of course, I mean, there's no barren plateaus in some way in the case of quantum annealers, but then they have the issue of the finite precision because it's kind of like an analog system that you're actually programming this more like this bias is directly there. So in reality, they work completely different. I would say the raise. So certainly the fact that actually in the gate-based model, I would say there is an advantage in some way in the sense that you could have more expressibility. For example, in the quantum annealing, if you look at the case of generative models, with for quantum annealing is mostly restricted to the case of the most kind of like exotic thing could be actually the quantum Boltzmann machine. And that's just because, but that still is restricted to the Hamiltonians that can be implemented on hardware. It's not actually a limitation of quantum annealing itself. It's just actually the physical realization. In the case of the quantum circuit board machine, and the reason why I see, for example, we can use it for these digits and work very easily with a few number of qubits, I would say it's just the power of what the circuit gives you to tap into the whole Hilbert space, relatively flexible. Of course, I mean, that comes with the caveat that the more expressibility you put in, the more difficult the model is to train. Yeah. But still, I mean, you get access to that, while actually in the quantum annealing case, you will need to maybe to design very sophisticated couplers that are very difficult and kind of like in the research frontier of quantum annealers devices. That is even beyond D-Wave devices. D-Wave themselves, they were trying to do this, for example, to add sigma X couplers to the Hamiltonians. Yeah. So all of this is technical, but as I said, at the end of the day, when it boils, if you're interested if someone is interested in deep diving into this question, of course, I mean, I would recommend look at the training. Actually, how is it trained in the quantum annealers and how is it trained with the classical models? That's where you find the Barren plateaus. And there also, the other component is about the expressibility. So how much of a diversity in quantum models, in probabilistic model, you can get from the gate base and from the quantum annealer. So there are pros and cons in each one of these components if you tease it out. But yeah, so I would say they both are heuristics at the end of the day. They both are quantum heuristics. I would not rule out that, for example, we can find maybe practical quantum advantage with quantum annealer first than actually with the case of gate-based devices, because I mean there's no free lunch. I think at the end of the day, and I think I mean the race is still out there, and I think it's So I will wait, I think, to make any calls before making any calls. But it's an exciting, I think. But they had different issues, and you have to be expert in both. I mean, it's difficult to.
Yeah, I think that's a great answer, right? Because I think that the question was coming from understanding how they differ, on which one is best, but how. So I think you did a fantastic job with that. Okay, so let's see if we can go through some other questions. DK02 Dennis was asking, I think it's a very open-ended question, right? So do you think that like your approach, I think in general terms, your research could bring an improvement to the bottleneck area of autoencoders? So I'm not sure what that means, but can you improve the bottleneck area of autoencoders?
It depends what is meant with the bottleneck area. For example, the variation of the encoders, like, for example, pre-training was one of the key things, or in deep belief networks. So it really depends, actually. So, I mean, it's hard for me to see exactly actually what the question is without actually knowing what's the bottleneck that is being referred. Okay. But if the bottleneck somehow is related, for example, like in deep belief networks, that is similar in some way, you have an encoding procedure similar to the one that we had there. If pre-training, for example, helps, that could be actually something that might be assisted with quantum models as well. But I think the emphasis of the last piece that I was trying to put is, if you focus in the latent space, and that's actually something that autoencoders also have, because you compress the data, and then actually you go out and you have the decoding phase. That is actually where I see most of the potential with quantum. So you might find some advantages by using quantum, but to be honest, I think one has to look really carefully at what is the reason for the bottleneck. Yeah.
Okay. Awesome. So there's a question. I want to read how it was stated, and then I'll try to interpret it. So the question is, what are the research gaps in quantum finance? And I think what is meant by that is, if you want to work in quantum finance, can you elaborate on like the role of the gap of knowledge between having to understand quantum computing and having to understand the problems that arise in finance?
Yeah, I think the work in quantum finance, as I said, it has been it's similar to the work in quantum machine learning. It has been some way kind of like divided in two camps, I would say. The one actually that is looking more like fault-tolerant approaches, or kind of like, for example, like speeding up Monte Carlo. For example, I think there is a talk tomorrow by Wilson, where actually, for example, in that particular case, where you expect kind of like a square root type of enhancement, square root type of speed up. So in that particular case, it's more like longer term, I would say. So definitely, I think that expecting actually that to happen in 5 years or so. The type of enhancement that we're proposing here, for example, the quantum enhanced portfolio optimization, is something that we could even do today. Actually, we're already talking, let's say, with financial institutions, with government agencies. And that's basically something that in principle, I don't need to wait, let's say, to already test the algorithm and to actually to show that hopefully that has an enhancement. So this is actually, it's kind of like the near term versus the other one. The other one, you can have a proof, but actually that it works in the long term. And for example, that's actually when the generation 0 of quantum machine learning algorithms, they were based on quantum speedups. The later they were debunked, but in principle, for the most part, that was the motivation. It's provable arguments that rely on quantum RAM and rely on the case of fault-tolerant quantum computation. That also exists in the case of finance. And for example, the key component is this amplitude amplification in finance for Monte Carlo, or the case of Grover search. So those are the kind of like the toolboxes for that research. And that is on the other side, the more like heuristic can apply. And that's kind of like the one that we are trying to also, that we navigate the most, just because we feel that it could bring value in the nearest term. But there is no actually right or wrong in some way. It's not like a gap per se. It's just kind of like the flavor of what you're trying to answer. So you're trying to answer and prove that you have a quantum speed up, then definitely go with something that is more tractable, something that you understand really well. If you want to kind of like make your bet and see you can have a quantum advantage in the near term, so then definitely you have to cope with the noisy devices, with the limited models, with the trial and error. That's actually how machine learning is developed. Yeah. When I talk to machine learning experts, they don't come to me and tell me, prove me that actually there's a speed up in all of these algorithms. If you look at most of the work of Josh Avenjo and Jeff Hinton, they're never proving speed ups. They're actually more like, okay, let's make these tweaks, and actually there's a motivation behind them, but actually that's how the research is done in that more like pragmatic approach. So I think they both are equally, I think, valuable and I think in their own camps, but they are trying to answer different questions.
That's right. I've always viewed this as a sign of progress in quantum computing, that we don't have to rely entirely on theory anymore, right? We have tools, like software tools, but also we have access to hardware, and so we can now start actually trying ideas and deploying them, and having empirical results dictate how good they perform, not just like theorems on paper. I think we'll go with one more question in the interest of time. I think it's a really good one. So Stefano is asking, Stefano, quantum-inspired methods like tensor networks are very powerful, as you showed. How do these compare with truly quantum methods, like running on a real quantum hardware? And in particular, how hard is it going to be for quantum computers to beat the classical but quantum-inspired methods?
Yeah, so that's a really good question. And to be honest, I think it really depends. So let's say in a fantasy world, like actually kind of our expectation, of course, is that when you have for example, even MPS, you can do universal simulation with tensor networks. You can actually reach out to simulate a full quantum computer, but that requires exponential resources.
Yeah.
So what I found really useful about this quantum inspired is that there is a progression that you can start adding complexity to your quantum models little by little. For example, you can go from MPS, maybe you can go to that is a one-dimensional model. Maybe you can go to a two-dimensional model, like the Mayer and Peps type of approaches. And then actually that adds more expressibility to the quantum model, but it still is relatively tractable. Of course, it's much more expensive, but it's relatively tractable without going all the way to full-blown quantum computation. So the promise for a quantum computation, for a quantum computer where actually would excel, is only in cases where actually your data happen to need those specific correlations that actually are not available within the tensor network, but happen to be within the axis of the larger exploration of the Hilbert space. At the end of the day, as I mentioned, at least in the first 10 years or so, I see it's still going to be very, very exploratory, in this very, very actually trial and error. In the sense, there is no guarantee that actually, although there are now beautiful results showing the separation between quantum models and classical models, there is still, there is no guarantee that the distribution that I'm going to come up with from finance, let's say, actually fits one of those. So actually, we still don't have a way to say that would be actually wonderful. If given the data, we could say, oh, actually, that's more like for a gate-based device. That's for a photonic device, and this actually you can do well with a quantum inspired, with a chip quantum inspired, with an MPS, and you can do actually like that. So we would like to have the magic separation between the problems. But the promise, at least, the fantasy land is, of course, is that the quantum model, the full quantum model is more expressible than just, let's say, the MPS. But even the MPS, if you add more bond dimension, you can simulate anything. It's just expensive. So it's just a trade-off of resources, how much you're willing to wait. and what is available to you, I think, at the end of the day. But in reality, it's it's just that the promise that the quantum models are different, and the MPS is different than the quantum gate base in principle. You're tapping into different Hilbert space.
I love that viewpoint, right? Because we tend to want quantum computers to be more powerful, and we sometimes forget that they're different, right? And that's also a lot that can be explored. So I think maybe that's a lesson for everyone in the chat. Okay, so one final question now, changing a bit of gears. Cool guy, this is Nathan. He's asking, Alejandro, how do you like it in Toronto?
Now I'm enjoying it a lot, to be honest. It's I mean, I think we love the city. These past weeks, actually, winter just started.
Yeah.
So now I hit minus 15, I think, consistently in the last 2 weeks. No, but overall, I think So
it's in Texas, so it's fine.
Yeah. No, I think it's I think overall it's a wonderful city. I think we like the vibe. So I think it's completely different from the Silicon Valley, from California. So I mean, there's plus and minus, but I think overall, so we love the people here as well, and so we're happy with my wife to be here.
Awesome, great to hear. Alejandro, so with Patrick, the previous speaker, I actually coincided with him when we were at IQC, right? And unfortunately, you and I have not really worked together, been in the same place, even though we're both in Toronto right now. But we have a common background, right? We have a common past of growing up in Colombia. So for me, it's always been very exceptional to put it into context, like that change of what science is like in Colombia, and then moving abroad and seeing how it's perceived and how it's done. So I was wondering if you could share a little bit of your story and what it was like growing up in Colombia and wanting to be a scientist, and how your path took you to where you are now.
Yeah, let's see if I can summarize. Yeah, in my case, actually, it's very special. I would say, let's see if I can summarize in a few minutes. In my case, actually, I happen to be, for my siblings, I had 3 siblings, and we happened to be actually the first generation that went to college. And this is something very special. My parents, actually, they were, as many of you know, in Colombia, there were really difficult times, particularly in the 50s, a lot of kind of the war and with the guerrillas. So actually, my family happened to be kind of in the middle of those difficulties, and went from the countryside all the way to the city. And then basically, for example, my mom, I think she still cries when she tells me the story. She really wanted to finish, but she couldn't pass actually elementary school. And my dad is the same. He finished high school when he was actually 40 years old. So actually, with my siblings and I actually happened to be first generation. And luckily, I mean, we all finished actually college, and then so 3 of us actually hold the PhD. So my path is a little bit unconventional, but I would say in Colombia, so the education system, I would say it was very, actually, I don't regret actually doing it, my undergrad in Colombia. So for example, I went for the PhD at Harvard. I think it gave me an excellent preparation for the program itself. I think Colombia is always, so it's always in my heart. It has a very special place in my heart. I go whenever I can. And I think it's definitely an exciting place to visit, and as well with really, really exciting science coming out of there with the team. Of course, less resources. I mean, it's not a country that is as fluent, but still, I think they do a great job with the resources that they have. I think that's my perspective.
Awesome. Thanks for sharing that. I really appreciate it. Okay, so now we're going to have a bit of fun. I've been preparing especially for this moment. Alejandro's a bit nervous because I gave him a hint of what's going to happen. So for Alejandro, if I'm not mistaken, you grew up in Cali, or at least close to Cali?
Yes, I grew up in Cali, yes.
Cali. So Cali, for those of you listening, Cali is the salsa capital of Colombia. I would even say it's the capital of salsa in the world. Maybe Havana can compete with it. And I didn't grow up in Cali. I grew up in Bogota, in the capital city, but I had a family that was living in Cali, and I would go often on vacation. And I remember everyone danced salsa. Just salsa is everywhere. My cousins had to learn salsa to be able to socialize with people there, right? Because they moved to Cali. And so it runs really deep. And Alejandro told us he's a big fan of salsa. He tries to dance and to enjoy it as much as he can. So what I want is to show everyone in chat right now how deep music goes when you're growing up in Colombia. So what I'm going to do is I'm going to whistle the tune of some very famous salsa songs. Alejandro has no idea what these songs are, right? But I am pretty convinced that I'm a good enough whistler and that the songs are so iconic that he'll be able to recognize them. So that's the experiment. Let's see how it goes. I'm going to whistle some songs. Let me do it for a while so people can kind of listen to it. and then see if you can guess them, all right? So here we go. And the chorus.
I think I can sing it. I mean, I don't know the name. I can sing it. I mean, I can sing, but yeah, so definitely. Yeah, I think it's called Kalyahi or something like that. It's
Oh, not so much. No, okay, maybe it didn't work so much. So that was a tune of a song called Oiga Mire Vea.
Oiga Mire. Yeah.
Mire Vea. A very famous song about Cali. All right, actually, okay, so maybe it's not gonna work so well. I'm gonna try another one. It's another song about Cali. I'm gonna give you a hint. It's another Cali song, right? Pachanguero. There you go. So when those brass music starts playing, there's just a cue for a lot of Colombians. Where
Well, Miguel, one funny story is that I think I only realized when I was maybe 22 years old that I left Colombia, that people was really surprised that I don't know. In my case, it wasn't surprising at all. That, for example, that when I would tell the story that at 10 years old, actually, we used to be in kid techs, it's just kind of like chicotecas. Yeah. So actually, that's there would be the dancing ball and everything. Of course, only soft drinks, but it was actually just I think maybe something in Cali. I think it's something special in Cali. But yeah, so when I was really surprised that people don't dance and people actually they're not passionate about salsa. And I think since I was 10 years old, it was actually you're dancing with your aunt when you're 3 years, 4 years old. Like they're trying to move you. So yeah, so it's a big thing in Cali in particular. So I don't know much about soccer, a little bit about coffee. I think I don't drink coffee that much, but yeah, definitely salsa is something that I really enjoy. And when I go back to my home, my parents are over 70, and I go dancing with them. So actually, it's a big thing.
That's amazing. Thank you for sharing that. And we have viewers from all around the world, and some people will be watching the recordings later on. So I like to be able to share how, like, there's also different stories, a lot of like origins for a lot of the scientists that all come together around the same ideas. So thanks for sharing that. I know, very well what it's like to come from Colombia and then find myself all the way in Canada in the winter. Alejandro, thank you so much for this amazing talk. I think we all enjoyed it a lot. Keep doing the fantastic work that you do. We're always cheering your team here at Xanadu, and thanks again. And for everyone else, we'll be back in just a few minutes.
Thank you, Miguel. Thank you very much.
Bye-bye.